Hello class, in this video we are going to be expanding our discussion of limits that we started last time. Last time was really just sort of an introduction of, the tool set that we're aiming for. Now we're truly going to define it and start using it and start getting down into the nitty-gritty of limits and how they work. Okay, so let's start with a bit of a reestablishment of what the limit is, and then we'll talk a little bit more about how we deal with it, what it truly is, all that sort of stuff. Okay, so the limit that we truly focus on in calculus is, well, we start with the function f of x, right? And so what we're saying is that the limit of f of x as x approaches a, so that's the value we're talking about, is equal to capital L if, as x gets arbitrarily close to a, f of x gets arbitrarily close to capital L. So here's how we notate this typically. Okay, we use the symbol, or not really the symbol, but the notation lim, L-I-M, x to a with an arrow, f of x equals L. So what we're saying is that the limit of f of x as x goes to a equals L. And what it basically is saying is that I prefer to write it like this instead of in words, that as x goes to a, f of x goes to L. Okay, I find that a little more visually satisfying, right? It makes a little more sense, at least to me. Okay, so a big question here is, what do we mean by arbitrarily close? There was Bertrand Russell, who was like a philosopher back in the day. He found it very frustrating that calculus classes in his day didn't really talk about what arbitrarily close meant or infinitesimal meant. So we're going to look at an example to kind of give you an idea of what we're talking about here, but there's more to it than that, and we will try to give a glimpse at the more rigorous discussion of what this means. But the idea is that we can get as close as we want to this number, right? But we're never actually getting there. All right, to give you an idea of what I mean by arbitrarily close, suppose 5 here, okay, is my a value that we were talking about, and here's a general x. Okay, there I've put it as a point here, but just think of x as the just the x component of this point. So what we're doing is we are bringing this x closer and closer and closer and closer, but the idea is that we're never actually getting there. Okay, because we can zoom in as close as we want, right, and still have a situation where we approach the a value here, right, and we could zoom in some more. Okay, and right, and that's as close as my program is going to let me get, because in the next step I'll be here. But the idea, and maybe I can adjust this, I can. All right, so here we're extremely close. We're 0.0001 away from 5. However, we can still get closer and closer and still never reach the point that we're talking about. Okay, So here, now we're 0.000001 away from 5. And we can continue this process over and over and over again. Right? So we could actually put our x here, and okay, and we can get closer and closer and closer. And pretend like I'm sticking on 0 there. But we can get closer and closer and closer and still never actually equal the 5. Okay, so here now we are this close to 5, but still not actually at 5. And we can zoom in even closer. I lost my point here. Okay, and closer, and closer, and notice this will never end, right? So this is what the limit is actually doing. It is analyzing what happens as x gets closer and 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 closer to a, but not what's actually happening at a. Okay, so the limit as x goes to 5 of f of x, it gives us how f of x behaves very, 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 very close to 5. That's why we use this little arrow instead of an equal sign. But also, we're talking closer than, say, 5 point, right? Closer than 5 point, all these zeros and a 1. Closer even than this crazy number. Say even with 1,000,000 zeros. All right, we are getting extremely close to, in this case, 5. And seeing what f equals. And this is opposed to f of 5. So this gives us what f of x equals at x equals 5. All right, so the f of 5 is when we have the equality. The limit is when we have the approaching 5. But remember, we get extremely close to 5. Okay, extremely, extremely, extremely close to 5, but we never actually get there. All right, I think of the limit as zooming in closer and closer forever. Now, this may seem kind of odd because you can't physically zoom in forever. All right, and that's what a lot of this module, a lot of this chapter, if you want to think of it that way, is about. The fact that, well, we can't just continue plugging in values closer and closer and closer and closer. There's got to be other techniques and other things and other ways to talk about limits that don't involve just plugging values in. Okay, of course, that's how we're going to start, right, dealing with these, just as a exploration of the topic. But there are much better ways to calculate limits. However, this is what's happening. This is what the limit measures. Okay, so a fair question is, well, why do we need limits? And it's essentially, right now, as we discussed in the last video, is to deal with indeterminate forms, right? Specifically, the one we're talking about right now is the 0 over 0 case. Because we can use limits in other cases. For example, we can calculate the limit as x goes to 1 of x squared plus 1. Right, so as x gets closer and closer to 1, x squared plus 1 will get closer and closer to, well, 1 squared plus 1, which is 2. There's not really a lot to talk about here if we have something that, right, exists. So f of 1 in this case would be 1 squared plus 1, which is 2. So this is a bit of a spoiler alert. Okay, but if f of x is continuous at a, or I guess I should say x equals a, then the limit as x goes to a of f of x is just f of a. Right? It's not really all that interesting because here I'll show you. Okay, here I've made a table of the x squared plus 1 and x, and I let x get closer and closer to 1. And let me... Okay, so as you can see, as the function, or as x gets closer and closer to 1, the f of x's get closer and closer to 2 and eventually equal 2. And because of this, okay, I can change the number of significant digits I'm looking at and start stepping up by 0.001. And as you can see, as we get closer and closer to this 1, our y values get closer and closer to the 2. Okay, now I increase the number of significant digits again. And again. And again. And so keep in mind, we don't typically want to use tables to evaluate limits because, well, you can see how close we have to get. But hopefully from here what you can see is that as x gets closer and closer and closer to 1, the y's are getting closer and closer and closer to 2, which should be obvious because when we plug in 1 into the function, we just get 2. So if we plug in something really close to 1 into the function, we should get something really close to 2 out of the function. And you'll notice here that a graph has shown up, and this is actually the graph of all these values. And you'll notice that it just looks like a point, okay, until we zoom in real close. Right, and now we're starting to see these values from the table. Okay. So as the x values here on this side get closer and closer to 1, the y values are getting closer and closer to 2. Now look at how close to 2 we are here. Most sane people would just round all these values to 2 anyway. Right? So there's... this may seem a little strange, okay, because why don't you just plug the value in? Well, in most cases you would, unless you're dealing with an indeterminate form. So let's actually look at that instead. Okay, where limits would most become useful, right, is in a case like this. So consider f of x equals the function x squared minus 1 all over x minus 1. So if we just try to plug 1 in directly, right, we would end up with 1 squared minus 1 on top and 1 minus 1 on the bottom. This would be 0 over 0, which is undefined. Right, so f is undefined at x equals 1. Okay? However, if we were to take the limit, we'll see something a little different. Okay, so let's think of the limit as x goes to 1 of f of x. All right, so a few ways we can do this. Let's look at a table first. Okay, so when I jump to this function in my graphing suite here, you can see over here that it actually graphs the function, and then note it puts a little guy here. Right, it looks like a little open dot, and that's exactly what it is. It says removable discontinuity 1, 2. Right, so that means that there is a hole here at the point 1, 2, which we should know that because when we try to plug in 1, right? When we plug in 1, we get 0 over 0, right? We get undefined. Okay? So let's take a look at a all right, so let's look at a table of values really close to 1. Okay, so I'm starting really close, 0.9999, and getting closer and closer and closer and closer and closer. And notice, in the table here, this is just software doing it, when we actually plug in 1, we get question mark. Well, that's because we can't plug in the 1. It's undefined, right? It's an indeterminate form. However, as we can hopefully see, as we get closer and closer to 1 from the left, it looks like our y values are getting closer and closer and closer to 2. In fact, if we zoom in here, and it will take us a while because we're really close. Yeah, there we go. We see, now we can kind of start to see the points. As the x's get closer and closer and closer to 1, the y's are getting closer. I keep clicking, there we go. We're getting closer and closer to this point here, which is the removable discontinuity. We'll talk a little bit about that later, but specifically these values, the y values, are getting closer and closer and closer to 2. Okay, now we're going to start on the other side. Values greater than 1, like 1.0001, and get closer and closer and closer to 1 from this side, right? So we're putting more and more zeros in, right? So we start over here at 1.001 or 0001, and we get closer and closer to 1. Again, when we plug in 1, we don't get anything. However, as we put more zeros in, okay, we are putting more zeros behind the 2. Okay, so it looks like, and then if we zoom in again, it takes us a while to get close enough. But as we can see from the right side, we have the same thing. As the x's get closer and closer and closer to 1, okay, the y's are getting closer and closer and closer to 2. However, all the way zoomed out, all we really see here is a point. All right, so from the table, it seems like, all right, so from the table, it seems as if the limit as x approaches 1 of f of x is equal to 2. Right, that's what we saw from both sides. Now, in general, when given a table, this is exactly how you go about evaluating what the limit is you plug in values closer and closer and closer, and you see what values the f of x or the y's are getting closer and closer to. All right, so if you noticed in the last example when we were plugging in values into the table, we sort of separated it, one from the left side, one from the right side, and we can actually do that just in general with the following notation. And evaluate them separately, which sometimes it actually makes a difference. So the limit from the left, which we call the limit as x goes to a with a superscript or the power of negative, this is when x goes to a but stays less than a. So I always think of this as if we think of it on a number line, that x only approaches from the negative side. Okay, this is the negative side of the number line, and x is approaching a from this side. However, on the limit from the right, it's with basically to the positive power. That is saying is that x goes to a and x stays above a. So on a number line, you can think of it as coming from the other side, right? Or x's stay on this side, right? So come in from the positive side of the number line, right? So from the negative side, or things lower than a, and from the positive side, things greater than a. So you can almost think of this as a lower, a greater. Right? So lower and greater. Okay? So a greater because it's a plus, a lower because it's a minus. Okay? Or a greater than a, less than a. All right, now before tackling another example, we'll say that the two-sided limit, which is the normal limit we've been talking about, it approaches a from both sides, and it only exists if the two-sided limits match. So this only exists if the left and right hand limits match. Right, so what do I mean by that? Well, let's take a look at an example here. Let's take a look at some limits involving this graph here, this sort of crazy graph. So how I want to start, though, okay, is just finding the limit as x goes to 1. All right, so we're going to find the limit as x goes to 1 from the right, from the left, and the two-sided limit. All right, so how we establish, say, the limit from the right, or from the positive side, as x goes to 1. So what we're going to do is we're going to look at what happens as x gets closer and closer to 1 from the positive side. All right, so I've set up this graph so we can take a look at what's going on, say, visually. But see, as x gets closer and closer to 1 on the x-axis, what we're doing is we're mapping it back up to the function f and then seeing what's happening to the y's at the same time. So remember what I said in the previous video, that calculus is all about analyzing how one variable or one quantity changes in relation to another. So what's happening here is that as x gets closer and closer to 1, f of x is mapping, if we look back over at the y is decreasing and getting closer and closer and closer and closer and closer to 1. And I have the values up here. So we can say that based on the graph, it looks like the limit as x approaches 1 from the right is 1. Okay, so we can go ahead and put that in there. It looks like we'll get the same thing from the left. Okay, and if we go from the left and do the same thing here, we seem to be getting really the same behavior as x gets closer and closer to 1 on the x-axis from the left side. The y is once again getting closer and closer and closer to 1. Okay, so we can say that the limit from the left side is also 1. And if things match from the left and the right, then the two-sided limit is the same thing. From both sides we get 1, therefore, well, from both sides we get 1. The limit is 1. Okay, now let's take a look at this other crazier value here, let's say -1. Okay, so we want to find the limit that x goes to -1 from the right, from the left, and that will also give us the two-sided limit. Okay, so now we're starting on the right side of -1. Now notice, I'm not starting all the way over at 0 or all the way over at 1. I'm starting halfway between, and really we should be even closer. Okay, but I'm going to go ahead and let this run now. And so as x gets closer and closer and closer to -1 from the right side, as we map up, we see that the f of x, the y's, as this happens, okay, y is getting closer and closer and closer and closer to 5. Okay, so that is what the limit from the right is going to be. All right, if I pause it right here at the very end, we see that when x is -0.999, y is 4.996. Okay, and when we take the final step over, right, at -1, we actually get a 5 because we have a closed dot there, right? So the function itself, f of -1, is actually 5. All right, so the limit from the right, as the right of, say, -1, is 5, and also based on the graph, f of -1, if we actually plug in the 5, you always go to where the closed dot is at -1. So there's an open dot, so we skip over that, and there we go, there's the closed dot at 5. Okay, so f of -1 equals 5. However, we're going to see some different behavior when we look at -1 from the left. Okay, so from the left, starting over here at x equals -1.5, mapping up to the y, let's, there we go, move that a little closer so we can see it, and we'll let this run now. And as x gets closer and closer to -1 from the left side, y now is approaching a different value. It's approaching this open circle, this open dot. Okay, so that open dot, the y value, as we can see here on the y-axis, is getting closer and closer and closer and closer to 2. Okay, so the limit from the left is going to be 2. Okay, so the limit as x goes to -1 from the left is going to be 2. And now this means that the two-sided limit does not exist. Okay, and so this is what we usually write for does not exist. Okay, to save us some time, whenever there's a jump in the graph, the limit does not exist. And you can see why that would be just by drawing any graph with, say, a jump. Okay, the limit's not going to exist because from the right side, right, when we approach it, we're approaching this y value, right? So let's say that's 1. But from the left, we're up here and we're approaching this y value, so maybe that's 3. So from the left, we approach 3, and from the right, we approach 1. Therefore, the two-sided limit does not exist. Okay, and so that's going to happen whenever there's a hole. But the left side and right side limits do exist, right? The limit from the left exists, it's 3, and the limit from the right exists, it's 1. So we could actually say that the limit, let's say this function here is g, the limit of g of x as x goes to, I never called this anything. Let's say that this is 2. Okay. From 2 from the left is going to be 3, while the limit as x goes to 2 from the right of g of x is 1. All right, so going back to the graph here, already here at 4, I know the limit doesn't exist. Okay, the limit won't exist because there's a jump. However, we can still analyze what happens on the right and the left. All right, to do so quickly, from the right here at 4, well, if I were to split this down the middle here, okay, with a different color, so I just drew a vertical line here at 4. On the right side of that is this line here, and it, as we get closer and closer to the line, its y value is getting closer and closer to 3. So I can say that the limit as x goes to 4 from the right is 3. Okay, if that doesn't help, I started plotting a bunch of points from 4.5 up to 4, and we can see this sludge here as we go from sort of right to left towards 4, it approaches 3. Okay, which we've now written here. The limit as x goes to 4 from the right of f of x equals 3. And now we're going to look at from the left. Okay, if we look at it from the left, well, on the left side of this line, we see we're approaching the y value of 2. Okay, and similarly, I just plugged a bunch of values in from 3.5 up to almost 4, and this is where we get closer and closer to this y value here, which is 2. Okay, so from the right, we have 3. From the left, we have 2. We, of course, know that the limit from both sides does not exist. Okay, so to summarize some of these things to make calculating limits from graphs easier, if f of x is continuous at x equals a, then the limit is just the same thing as f of a. Right? So, for example, if this was our function here, this was our f of x, and we're looking at 1 here, and that gives us a y value of, let's say, 3. Notice there's no hole, there's no break, there's no jump, there's nothing weird going on. This would be f of 1, which is equal to 3. So the limit as x goes to 1 of f of x is equal to f of 1, which is 3. And this will be the same thing as the left and right. Okay, this will match up from the left and the right. Okay, so that's if f of x is continuous. That's the simplest option we have. So like say here, right? This has like a sharp turn, but it's still continuous. So at 2, the limit should be 2 from both sides, and it is. Here at 0, the limit should be just 2 because the function's continuous there. There's no jumps, there's no craziness going on. Okay, on the other hand, if the graph has a hole with no jump, then the limit approaches the hole. Okay, that sounds odd. What does that actually mean? Okay, so let's say this is our graph here, and we have a hole here, then we have a hole, but that looks like a jump, but this isn't actually a jump. This is what's called a removable discontinuity, because what we've done is we've just removed a point from a continuous graph. Right, so in this case, all we've done is we've removed the point and moved it up here. Here, we've just removed the point. Okay, so notice that as we approach x from either side, on both of these, that the graph itself will get closer and closer to the open dot, right? So that's what I mean when I say that the limit will approach the whole. So let's say these y values are 1, 2, and 3. Okay, so in this case, the limit as x goes to 2 of f of x, it's going to be 1. It's approaching that whole. F of 2, right? Well, there's a hole. There's no point, so that's just undefined. Okay. On the other hand, the limit as x goes to 4 of f of x, okay, well, it's going to be approaching the whole. Now, the whole is at 2. So that's going to be 2. However, f of 4, well, that's where the actual point is, and that's 3. So this function is not continuous, however, the limit exists. So here, in both of these cases, the limit exists, but the function either doesn't match or doesn't exist itself. Okay, and this is going to be a really common occurrence because these holes, they always, well, maybe not always, but they typically show up whenever we have 0 over 0 happening. All right, that's just where we have an empty spot versus here where we just moved it. But typically, 0 over 0 cases tend to give us holes in the graph. Not always. Okay, we'll see cases where that's not always the case, but sometimes it will lead to blow up, right, asymptotes, that kind of thing, but a lot of times it gives us holes in the graph. All right, now if there is a jump, like a full-on jump, then the two-sided limit does not exist. Okay, so for example, this function here, we have a jump, and so let's say we jump from, let's say that's 2 and this is 4. Okay, so now notice it's not the same as what we saw up here, because this just jumped for a point and then came right back down, right? So this is almost continuous, while this is a straight-on jump. These two sides do not align. So from the left, right, the limit from the left here is 2, and the limit from the right is 4. Okay, and the two-sided limit, of course, does not exist. Okay, here though, f of 5, right, the actual f of 5 does exist because we have a closed point here. Right, so when we plug 5 into f, we just get 2. However, over here, f of 10 is undefined, right, because there's no closed dot anywhere. And the left side, let's just say it's also 4 and 2. Let's just say it lines up. But here the limit as x goes to 10 from the left is also 2. And the limit as x goes to 10 from the right of f of x is 4. Okay, but this is sort of the difference. If there's a closed dot on one of the ends of the jump, f of that value will be defined. Like in this case, f of 5 is defined as 2. Otherwise, it will be undefined. And you can see a situation where you have an open dot, and a closed dot somewhere else. That's an even crazier situation. So you might see something like this with a closed dot in between. Okay, so this is, let's say this is 15. This is f of 15. This would be the limit as x goes to 15 from the left. And this open dot would be the limit as x goes to 15 from the right. Okay, so that is the the difference between these. Now, if these two sides lined up, that would be the two-sided limit, but when you have a jump, it doesn't exist. All right, so it may seem pretty obvious at this point that our ability to deal with limits is pretty hampered. I mean, from this section, all we've really looked at are tables, which are very problematic, which we'll talk about why in a little bit, and graphs, which also can be a little problematic because you saw how far we would zoom in, and because of that, there's no telling what the graph may be doing as you get closer and closer and closer. But right now, those are really the only tools we have. Okay, so in the next lecture, we're actually going to talk about algebraic ways that we can calculate limits. That's really going to help us out a lot more than just using tables or graphs. Okay, so that's going to be the next lecture. What I do want to do in the time that we have left in this particular video is give a little more of a stronger definition of what we mean by arbitrarily close. You've seen it you've seen it in on the graph as we zoomed in. I want to give something a little more rigorous. This is not what would be considered an official definition, but it's pretty close. Okay, so here's how we officially talk about arbitrarily close. Okay, so for the Bertrand Russells out there who maybe don't like this idea of just saying we get arbitrarily close, how do we deal with that in a more official way, a less wishy-washy or hand-wavy way? Well, here's how it's done. Okay, so when we say that the limit of f of x as x goes to a is equal to a, we're basically saying that if we want the distance between f and L to be within a small tolerance t, then we can always, and that should be specified, we can always, right, find an interval around a where x's in that interval will cause this tolerance to happen. Okay, well, what do I mean by that? All right, well, first of all, the distance between f of x and L is given by this. It's the absolute value of f of x minus L. That's the distance between any two things on the number line, right? The absolute value of a minus b, that's the distance between a and b. Okay, and we want that distance, say, less than t. I'm using t for tolerance, right? And we want this to be small as we want it to be. The idea is that we can find, right, we can find an interval around a where this is guaranteed to happen. I think it's easier to describe what's going on here with an example. So let's look at that example we started with, or one of the examples we started with, right, which was the function x squared minus 1 all over x minus 1. We found through the table and looking at the graph that the limit as x goes to 1 of f of x is equal to 2. Okay, so what this means is that the distance between f and 2, all right, which would be the absolute value of f of x minus 2, if we want this say we want this less than 0.1. We want the distance between these two values less than 0.1. We should be able to find an interval where this happens. Okay? And how we do that is we play around with this a little bit. Don't feel too bad if you're having trouble following this. This is just an explanation piece, but if we replace the function with its value or its definition here, and then we factor the top, right, that's x plus 1 times x minus 1, all over x minus 1. Well, the x minus 1's cancel, right? And then we're left with x plus 1 minus 2, which will be the absolute value of x minus 1. Now this is the distance between x and 1, right? So these things are equal. So if we want this to be less than 0.1, we essentially want x minus 1 to be less than 0.1. Okay, now if you remember from pre-cal or algebra, when you have an absolute value inequality like this, it changes to the x minus 1 being trapped between negative 0.1 and 0.1. And now we can just add 1 to both sides. Right, to cancel it out. And so now we have 0.9 is less than x, which is less than 1.1. So what we're basically saying here is that as long as x is in the interval negative or 0.9 to 1.1, then f of x minus 2 should be within our tolerance, which is 0.1. Okay, so let's see if I pick, let's pick x as 0.95. Okay, f of 0.95, that will be 0.95 squared minus 1 all over 0.95 minus 1. Let's see what we get. All right, I got 1.95. Okay, so f of 0.95 minus 2, when we take the absolute value, that will be 1.95 minus 2, which will end up being the absolute value of negative 0.05, which will be 0.05, which will be less than 0.1. Okay, well, what if instead we wanted the distance between f and 2, instead of less than 0.1, we want it less than 0.01. Well, we would do the same work over here. That's the same thing as wanting the absolute value of x minus 1 less than 0.01. Right, so all these would just change now to 0.01s. So we'd end up with 0.09 and 1.01. Okay, so really we are looking at the interval from 0.09 to 1.1. Okay, and so in this case, if we did like let's do 0.0, let's do 0.5, right? That would be in between here. Sorry, I messed that up. That's 0.99. Okay, 0.99, not. So let's do 0.995. Okay, when we do that, we get 1.995. And so if we were to plug that in, we should get negative 0.005, which will be 0.005, which will be less than the 0.01. So essentially, if we want the f of x minus 2 less than any small value, okay, that corresponds with wanting x minus 1 less than that small value, which ends up meaning that we want x trapped between 1 minus that small value and 1 plus that small value. Okay, so if the tolerance we want is like 0.00001, then we want x in between 1 minus that and 1 plus. Okay, but no matter how small t gets, we can always use the interval, say use the interval, 1 minus t to 1 plus t to get within that tolerance, right? To get that close. So that's what we mean by arbitrarily close to. We can let the distance between f and its limit get as small as we want, and if the limit exists, we can always find an interval around, in this case 1, that will make that work, that will let us get that small. This is the official math way of basically saying we can zoom in as far as we want. Okay, so don't get too hung up if this feels a little out there and abstract. It is. This is more what's going on behind the scenes. We aren't really going to mess with this that much. Okay, we're instead just going to jump to the algebra we can use to help us out. However, this is needed to at least be somewhat convincing, right? The thing about adult math, right, is that everything has to be verified. Everything has to, if not be proven, at least have some sort of rigorous foundation. And so this is the rigorous foundation of what we mean by get arbitrarily close to or zoom in as far as we want. What we're essentially saying is that no matter how close f gets to 2 or how close we want it to get to 2, we can always find x's that will satisfy that. Okay, so that's all that is. And with that, I will close down this particular video and I will catch you all in the next one. Cheers!